Okay, today I want to talk a little bit about Schrodinger's equation. Now, this is an equation that comes from quantum mechanics, and I don't want to scare you away with the mathematics, but I feel videos like this are very important to do. There's a lot of videos on YouTube, Facebook, and they're very pseudoscientific. They use terms from quantum mechanics, and they really have nothing to do with quantum mechanics at all. Things like quantum healing and stuff like that. And the truth is, actual quantum mechanics is far more interesting. So I just want to give you a little taste of this. And again, I don't want to scare you away, but I'm hoping that this might entice you. If you're thinking of going into this field, it might show you some of the neat kind of things that we can do with quantum mechanics. So for starters, I'm going to erase this so we have a fresh board. And we're going to start at the beginning. So one of the postulates of quantum mechanics, aside from things being quantized, which is where the name comes from, is that particles, photons, electrons, etc. can be represented by a wave. Now, in mathematics, how we describe a wave is with a sine or a cosine function. So sine of x, for example, would have a wave like this going from 0 to 1 and oscillating. Now, we can modify this wave in a number of different ways. So let's say, for instance, I have capital A times sine of b times x plus c. Now what this value out front does is it multiplies the entire thing by a, which means it stretches this value this way. So you take the entire wave and you stretch it this way. You increase its amplitude. The b here acts on x. So what it does in essence is it'll expand or contract the entire wave horizontally. And last but not least, the c value here displaces it from right to left. So these ways of manipulating waves are going to be very, very useful later on. Now, in quantum mechanics, we use a nifty little function, and it's called Euler's formula. And basically, Euler's formula, it uses something called complex numbers. So maybe I'll explain that a little bit. A complex number is something multiplied by I, and I is defined as -1. So this seems a little bit strange because we all know that you can't take the square root of a negative number, but still, you can use this as a mathematical concept and you can do things with it. Let's say simplest thing, I squared. Well, we know this is going to be the square root of -1 times the square root of -1, which is just going to be -1. So we end up getting a real value from something that's imaginary, and that's actually what it's called. It's called an imaginary number, I. So we're going to use this now. We're going to take e, which is an exponential function, to the power of I times theta. And what Euler found out is that this is equal to cosine theta plus I times sine theta. So you have kind of a composite wave that has a real part and an imaginary part. So just as we can describe a particle or whatever as this kind of wave, a particle can also be described as some composite of different waves, whatever. That's an equal, valid explanation, basically. So why do this? What do we get from here that makes it easier than just dealing with sine? Well, basically, later on, we're going to need to do things like derivatives to the function. And what we find is that doing a derivative to an e function is very, very simple. Let's say I have d of dx of e times 2x. All you do is you take this constant up here and you drag it out front. So we end up getting 2 times e and then of the same function, basically. So this makes for very, very easy derivatives. We have a way of taking the wave function and putting it into something where we can do operations like derivatives very, very easily. So it comes in useful. So the next thing I'm going to do is I'm going to write down something called the wave function. And the wave function is going to be our starting point in deriving Schrodinger's equation. It's going to seem a little precarious at first, but I'm going to explain somewhat as best as I can in this short amount of time what it is. So the wave function is denoted by Greek symbol phi, and it depends on x, which is position, and t, which is time. Now, first thing, we have this constant out front, which might seem a little weird, but this is a property of Fourier transforms, basically. We have two values. We have phi, and we're going to have the amplitude of the wave too. And basically all this is just the constant we put out front so that we can put them in terms of each other. They can be interchangeable. Again, this might seem a little bit abstract, but it's not the most important part of this. It's something I might explain in more depth in a later video, but it's not the crux of this video. So just know this is a constant that's out front. Doesn't really have a whole lot of effect on the function itself, but it's just there. It's not the meat of the equation. Now this is going to be an integral from negative infinity to positive infinity of a of p. So what's that? Well, a is the same a that we saw before when I took this a sine of bx plus c, that little function I made before. So basically this modulates the amplitude. And p is going to be momentum this time. So instead of using artificial variables before, we're now dealing with actual values. So p is going to be the momentum of the particle. We're going to times this by e to the power of I. So this is our way of creating wave functions here. This is our e to the power of the imaginary number. And instead of just putting theta here like we did before, we're going to put px, so the momentum of the particle, times its x position, minus e of t, where e is energy. So basically, e is being multiplied by time. And if you remember, what this part did here was it moved the wave back and forth. And this kind of makes sense, because if you think about it, if we're talking with respects in time, as time moves forward, the wave is going to propagate in one direction or another. So that kind of makes sense, doesn't it? And this is going to be divided by h bar. Now again, this h bar comes in because things like the wave function, they act at very, very small scales, and h is a constant that is very, very small. It's called Planck's constant. And we deal with this a lot in quantum mechanics just because things like this happen at very, very small scales. So that's what this thing is. It's just a very, very, very small constant that we use quite often. And then all this is multiplied by dp, because we're doing an integral here. So basically you can imagine this a bunch of little dp's being added up throughout the range of the integral. Now, what's the first thing we do? Well, we want to make something that corresponds to this with respect to position and time. So like I said before, derivatives are very, very easy to do with something like this. So let's take a derivative. Let's do a partial derivative of the wave function with respect to time. So we have partial derivative, which is this kind of almost like a 2 type of thing, but not quite, of the wave function with respect to time. Now what happens here? What are we going to get when we take a derivative of this with respect to time? Well, what's linked to time here? We have an e out front, and we also have the I, because remember this is in brackets, so you're going to have to multiply this out, and we have an h bar over here. So basically, if we remember, we can take something like this, and if we take the derivative of it, we end up pulling this constant out. So we can do the same thing here, whatever. We can take all these constants that are linked to t, and we can pull them right out front of here. That's what we can do. So let's do that. We're going to have a factor of e and I in the numerator, and this negative symbol is going to go with it. So let's write that down. I'm going to have negative I over e, and in the denominator, we're going to have a factor of h bar. So let's pull that out. And then this whole thing is still going to be the same, whatever. It's going to be multiplied by the exact same thing. So it's going to be a wave function. So this is all multiplied by phi. Now the next thing we're going to do is we're going to take a derivative with respect to position, but this time we're going to take a double derivative. And this seems a little strange, whatever, but you'll see why it works later on. So now we're going to take the double derivative of the wave function with respect to x this time. And what is this going to do? Well, what's connected to x? We have p, we have an I, and again we have an h bar. But this time it's a double derivative, so we're going to do the function, we're going to do the operation twice. So we're going to get a p squared and I squared, which is going to be -1, and we're going to get h bar squared there. So we're going to write this down. Basically, we're going to have, what did I say? I squared, which is -1. We're going to have p squared. Okay, so yeah, -1 times the p squared is just going to be negative p squared. So we'll simplify that a little bit. Over h bar squared, and again, this is going to be multiplied by the original function, which is phi. So now we can kind of see what we can do here. This is obviously equal to this, whatever. So what if we take these two equations and put them in terms of phi? So let's rearrange this a little bit. So we have phi is equal to this, the partial derivative of the wave function with respect to time, times negative h bar over IE. So basically I just took this and I flipped it and put it on the other side or whatever to get in terms of this instead of this. And we're going to do the same thing over here. What is this equal here? We're going to have phi is equal to the double derivative of the wave function with respect to x times negative h bar squared over p squared. So because this is equal to this, that means this is equal to this. So I'm going to erase a little bit up top just so I have some room. The great thing about video is if you're writing this down, you still have it. Okay. So we're going to write this is equal to this. So we're going to have, try to write up high so I have enough room. Partial derivative of the wave function with respect to time. And another thing I'm going to do is it's going to have a negative value over here and a negative over here. So those just cancel out. So I can put this in terms of a positive value. So this times h bar over I times e is equal to the double derivative of the wave function with respect to position times h bar squared over p squared. Now, what I'm going to do next is I'm going to take a classical formula for energy, and I'm going to insert it into here. So you guys might remember, if you took any classical physics, that energy is equal to p squared over 2m plus v, the potential energy. So we can use this now. Because E is equal to that, we can put one side of the equation over here and the other side over here. So let's put E over here. Multiply this by E, and we're going to take p squared over 2m plus v. So this side is done, and we're going to have to multiply this out. So let's just do that. Let's take, well, what do we have here? We have an E in the numerator and an E in the denominator. So these simply cancel out. Done. And if we multiply this out, okay, so let's rewrite this. So we have times h bar over I is equal to, now we have this times the first part here, which is p squared times p squared over 2m. And we're going to do the same thing with the v, so we're going to times this by the v as well. So we're going to have plus double derivative with respect to position. Sorry, I'm trying to write my partial derivatives not like 2's, because I have a 2 here. I don't want to confuse you there. H bar squared over p squared times v. And also here we have something that we can do. We have a p squared in the numerator and in the denominator. So these two cancel out. And if you notice, right here, what we have is this exact thing right here. And we know that this, with a negative sign, is equal to phi. So what we can do is we can replace this with negative phi. So basically, if we cross this out, we can say that this is equal to negative phi. So that helps us simplify things a little bit. So let's rewrite this out so this doesn't look so messy. We have partial derivative of the wave function with respect to time times h bar over I is going to equal partial double derivative of the wave function with respect to position times h bar squared over 2m. And this is going to be, yes, plus v times the wave function. And I'm going to erase this just to leave a bit more room. Oops, sorry. And because the sign switched or whatever, we needed to put the negative value in there. So that's a little mistake there. So this is actually minus. Now, this is almost done, but for convention, for whatever reason, they write things out a little bit differently. And to get the final result of Schrodinger's equation, we're just going to multiply each side by I squared. So it might seem a little bit arbitrary, but I think it makes things a little bit neater. So let's do that. What's I squared times this? Well, we have an I squared in the numerator and an I in the denominator. So one I cancels out, and we're left with one I in the numerator. So we're going to get, and I'm just kind of switching positions here. So it's the same thing, but I'm just putting the IH in front, times partial derivative of the wave function with respect to time is equal to, what's I squared times this? I squared is negative 1. So it's going to flip the sign of this and turn this into a negative. So negative partial double derivative of the wave function with respect to position times h bar squared over 2m. And same thing here, I squared is equal to negative 1, so it's going to flip the sign here, plus v phi, which is potential energy times phi. And there we have it. Schrodinger's equation. We have a nifty little thing that relates position and time that we can use for like particle in a box type of equations and stuff like that. And I might go into how to use it in further videos, but just to kind of give you an idea of how something that's like an actual quantum mechanical equation is derived. And yeah, I'll do a video next time on how to use this, but that's it for now. Thanks.